really like this next problem because it really requires us to understand what's going on. We have a red graph, which is p of x, and we have a blue graph, which is m of x. And when we are being asked to find m plus p of 1, that basically is saying m of 1 plus p of 1. The two values, m is the blue graph, so at 1 the heights are going to be 4 plus 2, so we will have 4 plus 2, which is equal to 6. In part B, p minus m of negative 4, that will be red minus blue. At negative 4, red is at a height of 4, blue is at a height of negative 2. So we will have 4 minus a negative 2, which is also going to be 6. For part C, m over p, that'll be blue over red of 3. That'll be height of 2 over height of 0, so 2 over 0 equals undefined. M times p of 3, well, that'll be 2 times 0, because we've already found those values out in part C, and that will equal 0. M composite p of 0. Now this is the interesting part. We start by substituting 0 into function p. That will be a height of 2. Then 2 goes into function m. So we have m of 2. We take function 2, go up to the blue graph m, and find out that its output is a height of 3, and the final output there is 3. Now in part F, 0 is going to get substituted into m first. 0 into function m gives us a height of 4. 4 then gets substituted into p. P of 4, okay, let's go to 4. P is down a unit, but there's an open circle there, so that's going to be undefined. P of m of negative 4. Negative 4 first gets substituted into m. So here's our negative 4 down to m, that's a height of negative 2. So negative 2 gets substituted into function p next. And p of negative 2, go over to negative 2, up to graph p, which is in red there, and the height is going to be 4. Something that catches my attention, notice in problem E and F, m composite p and p composite m do not give you the same result. That tells you that the composition of functions is not necessarily commutative. You can't reverse the order and necessarily have the same result.